Our next lesson is going to be on percent composition. This is percent composition number 2. In this lesson, we're going to look at finding the molecular formula from the empirical formula, and we're going to look at something called structural formula. And so, to find the molecular formula from the empirical formula. One of the things that we talked about in the last lesson was how that if we have percent composition by mass, we can use that to find the empirical formula. That is the simplified version where we just have the basic ratio of the elements to each other. And so what we're going to look at here is basically at using this to find finding the molecular mass, because that empirical formula doesn't tell you what the actual compound is. It just tells you the ratio of the elements in the compound. So to find what the molecular formula is, what we need to have is the molecular mass. And so if you're given an empirical formula, you either need to find some way of actually calculating what the molecular mass is, or measuring it, or you'll have to be given it. And so once you've got that, this is basically what you're going to do. You're given that molecular mass, or you find it somehow. And so the next thing you want to do is you want to find the mass of the empirical formula. That is, you're going to take the empirical formula, add up the different pieces the same way you would if you were finding a molecular mass. Only this is not technically a molecular mass because it's not a molecule. An empirical formula is just like the reduced form of a molecule. And so like if we had an empirical formula that was CO, then that would mean that we'd basically take that. We take the mass of C plus the mass of O, because we have one C and one O, add them up, and that would give us that empirical mass. That's the mass of the empirical formula. Once you've got that empirical mass, you want to take the molecular mass and divide it by the empirical mass, and that'll give you what's called the scaling factor. That scaling factor then can be multiplied times the numbers in the empirical formula to give you the final one. It sounds a little confusing at first, but let's actually work it out by doing an example. So in this example, we have an empirical formula is OH, and so that's our empirical formula. We're told the molecular mass is 34.01. So to do this, here's what we're going to do. We're first going to find what the mass is of OH. And so to do this, we say we have how many oxygen molecules, or how many oxygen atoms. We have 1 in OH. We're going to multiply that times the mass of oxygen. If you look that up on your periodic table, you see that 16.00. And then we're going to take that and we're going to add it to the number of hydrogens. That's just 1 times the mass of a hydrogen atom. That's 1.01. It's like that. And if we do these two together, we say 1 times 16 plus 1 times 1.01. We add them up. We get 18.01 is what we get for the total mass here, the molecular or the empirical mass. So that's the first part here is we get that empirical mass. Then we're going to do, as we said on this section right here, divide the molecular mass by the empirical mass to find the scaling factor. So the molecular mass, we said, was 34.01. So 34.01 divided by that empirical mass, 18.01. And so, let's show you, that's not 18.01, that should be 17.01. That's a mistake that I made there. Let me fix that here. Take that across here and get rid of that right there. Apparently, that's what I get for doing this in my head, not using the actual calculator. That should be 17.01. And then this down here should be the empirical mass is 17.01. And so we say 34.01 divided by 17.01. And if you do that, you get something that is just barely slightly under. It's 1.99. And so this gives us basically 2. And so our scaling factor is 2. And so if we had this, we have, since the empirical formula was OH, we would have, instead of O, we'd have O2. Instead of H, we'd have H2, because we scale them both by 2. So this would be our molecular formula. But, as we said in the previous unit, that we always want to make sure the cations first. Oxygen has a valence of -2. That's got to be an anion, so we've got to flip these around. Hydrogen can be positive, and so that means that we're going to end up with our final one is H2O2. And so this is our final molecular formula. And if you recognize this, you'd say that's going to be hydrogen peroxide is what the name of that guy is. And so that's how you find the molecular formula from the empirical formula. Let's try another couple as examples here, just some practice ones here. And so let's suppose we have an empirical formula of CH2O and has a molecular mass of 180.16. First step is going to be, as we did before, is let's find what the empirical mass is. We have 1 carbon, so we say 1 times the mass of carbon, 12.01. And then we're going to add the number of hydrogens. There are 2 hydrogens, so 2 times the mass of hydrogen, 1.01, and then plus, that's a 1, not an 11, plus we have 1 oxygen, times the mass of oxygen, which is 16.00. And so if we go ahead and get our calculators out on that, we say 1 times 12.01 plus 2 times 1.01 plus 1 times 16. We do that, we get 30.03. And so 30.03 is our empirical mass. So then what we want to do is we want to go and take that molecular mass, which is 180.16, divide it by that empirical mass, 30.03, and we go ahead and do that. And if you run those numbers here, we get something that is just slightly under 5. And so 5 is our scaling factor. And so it's late here. 6 is what we get. 180 divided by 30 is 6, not 5. I really do need to use a calculator, not do it in my head. So I get 6 for this one. And so as a result, that my molecular formula, since my empirical formula is CH2O, my molecular one is going to be C6H12, because 2 times 6 is 12, O6. And so that is going to be my final empirical formula, my final molecular formula. Note that we didn't really look for which one was the cation here. It's sort of difficult to tell on this one. Carbon can be a cation, hydrogen can be a cation, oxygen can't. This particular type of formula, one that has carbon, hydrogen, and oxygen in it, is actually called an organic molecule. Organic means it contains carbon. And usually has chains of carbon. There's lots of carbons. Here we have 6 carbons in this one molecule. We're really not going to discuss these in too much depth in this class. Don't really cover too much organic chemistry, but just sort of be aware that organic molecules like this typically use a different system, both of naming and of writing them out than other ones are. And so if you get one that's carbon, hydrogen, and oxygen, and there are lots of carbons in it, it really is okay if you just write it out. Just put the carbon first. Is usually what you do. It's usually a carbon first type atom. The rest of them you can sort of fill in there. I'm not gonna sort of hold you to finding the cations on these because it's really difficult to find a cation in organic molecules like this. And so don't worry about it if you have one like this that it's not clear what the cation is. Just go ahead and write it out, and you'll be fine with that. Let's take a look at our next one here. Empirical formula is H2SO4. The molecular mass is 98.08. And so first step here is, once again, let's find what the empirical mass is. I have 2 hydrogens, so 2 times 1.01, and then plus I have 1 sulfur. And so I say 1 times, you look at the periodic table, the mass of sulfur is 32.07. So I have 32.07, and then plus I have 4 oxygens, so 4 times 16.00. And so if we do this time I will use a calculator. What we find is that 2 times 1.01 plus 1 times 32.07 plus 4 times 16. And when you do that, you get a total of 98.09. So that's what we get for our empirical mass. So once we've got that empirical mass, the next step is going to be to take that molecular mass, which is 98.08, and divide it by the empirical mass, 98.09. And what you notice here is that this is basically 1. This is one of these cases where the empirical formula and the molecular formula are basically the same thing, and or are the same thing. Is that the molecular formula is its empirical formula? So our answer is just this H2SO4 right there. That is our final answer on that one. It is both the empirical and the molecular formula. And if you ever find that your molecular mass is the same as your empirical mass, it means they're just the same formula, and so it saves you some work there. Let's go on and take a look at our next topic, which is going to be on structural formula. So, structural formula, the basic idea we have here is our previous formula we've had. The empirical formula shows you the ratio of the elements in the formula. The molecular formula shows you how many exactly there are, not just the ratio, but the total number of each element in a compound. The structural formula not only shows you number, not only shows you ratio, not only shows you number, it also shows you where the atoms are, like what their physical structure is, where they are related to other ones. And so, so number one, the basic idea of the structural formula is it shows the physical structure of the molecule. It uses bonds to show connections between atoms. And so, to give you an example of how this works, let's take water, good old H2O. And so if I have water, H2O here, if I want to draw the structural formula for this, what I do is I would use bonds to show this. And so the structural formula of water, I have an O, I have two bonds that come out of this, and on the end of those bonds are where my H's are, my hydrogens. So this would be the structural formula of water. That bond, that sort of that line that connects between the hydrogen and the oxygen right in here is those guys right here. Those are your bonds. Basically what they're doing is that they are basically showing you these two are connected. They're sharing electrons is what's happening. That they have basically as they've gotten close enough that they're able to share electrons across there. And so that's the reason why they bond here. So it uses bonds to show connections between atoms. The way this basically works is the number of bonds for each atom is the same as its valence or oxidation number. So if you take a look at oxygen on your periodic table, look at its valence. It has a valence of -2. So because it has a valence of -2, it has how many bonds? It has 1 and it has 2 right there. And so it makes 2 bonds because it has a valence of -2. We don't really worry about the negatives on here. We just look at how many it's going to make. That means it's going to share 2 electrons, and so it's going to make 2 bonds. The hydrogen, each hydrogen has a valence of plus or minus 1. It has to be plus 1 in this case. And so it's going to make 1 bond. And so this hydrogen makes 1, this hydrogen makes 1. And so as a result, that works out. And so the number of bonds for each atom is the same as its valence or oxidation number. Let's see. Another way that you might sort of look at this would be to look at CH4. And so if I have CH4 like this, here is one of the ways it would work here, is that to write this out is to start off with carbon. I have 1 carbon here. Carbon, if you take a look at the periodic table, has a +2, +4, -4 as its valences, is that typically it's going to be -4 for this. And so as a result, carbon will make 4 bonds. And that's just something you sort of just need to know, is that in general, in the vast majority of cases, when you draw a structural formula, carbon's going to have 4 bonds because it's normally -4 for its valence. And so it makes 4 bonds, that makes it going to make 4 connections off of it. And so it makes 4 bonds like this. So we have 4 hydrogens attached to that, since it's CH4, and so those 4 hydrogens are just going to go in each one of those bonds. There's 1 hydrogen here, 1 there, 1 way up top, and then 1 over on the side. So if you look at this, then what you can see is that the carbon has 4 bonds, which it wants to, so it's happy. Each of the hydrogens only has 1 bond, so it's happy. We have 1 carbon and 4 hydrogens, so everything's nice and hunky-dory. And so this is how you draw out the structural formula for CH4. Now the next one. Atoms may form double or triple bonds with other atoms in a compound. Is that there are, instead of just having 1 bond from an atom to another atom, it is possible to have 2 bonds. This is called a double bond. Double bonds are much stronger than normal single bonds. They typically result in the atoms being closer to one another. Basically what's happening is that they are sharing 2 sets of electrons rather than just 1. And so a double bond is typically drawn by showing 2 lines rather than 1. Classic example of this is carbon dioxide. And so carbon dioxide, CO2, what happens here, we have 1 carbon and we have 2 oxygens. The carbon wants to have 4 bonds, but only has 2 oxygens to share those with. And so since it only has 2 oxygens, it's going to make a double bond with each oxygen. And so what we'll get is we will get this guy right here. This is the structural formula of carbon dioxide. Does each of the oxygens have 2 bonds like they want? Yes, because oxygen has a valence of 2. Does the carbon have 4 total bonds? Yes, it does, because its valence is 4. And so this would be what carbon dioxide would be. It is also possible to have said triple bonds. Classic example of this is nitrogen. Nitrogen is a diatomic molecule. That is, whenever it's in a free state, it's by itself. You just have nitrogen gas, is that it forms N2. The ones who tend to do this are the elements which have endings in GEN or INE. If the element's name ends in one of those 2, then when it's in a free state, it will be diatomic. Hydrogen, when it's by itself, is H2. Oxygen, when it's by itself, is O2. Fluorine, when it's by itself, INE, is F2. Iodine, when it's by itself, is I2. So nitrogen, N2, is this guy right here. Whenever I have 2 nitrogen molecules, though, if you look at it, it says on the periodic table, I got 2 nitrogens. They have to bond together. On the periodic table, it tells me that nitrogen generally, we said, has a valence of -3, right? That's its most common one. That means it's going to make 3 bonds. Well, it's only got 2 of them, so that means those 3 bonds are going to be a triple bond between these 2 nitrogens. And so that nitrogen bond is extremely strong. And so when you're inhaling, as you inhale right now, You're inhaling all this nitrogen. That's 79, 70 something percent of the atmosphere here. I think it's 78% roughly. You're inhaling a lot of these double-bonded nitrogens. They're really tight together, and this actually is one of the reasons why we have to fertilize soil, is because these nitrogen bonds are so tight, it's very difficult for plants to get the nitrogen that they need. It normally has to happen basically through various biological means if it isn't done through fertilizer. And so we use fertilizer instead to basically get the plants the nitrogen they need without having to break that incredibly strong triple-bonded nitrogen. So it is occasionally possible to have something that has quadruple bonds, but that's pretty rare, and we're really not going to go there. All right, next one up here. It is possible for atoms to have the same molecular formula, but have different structural formula. That is, they have the same number of atoms of each type of atom that's in there, but that when you actually put them together, they actually have a different structure to them. These two types of formula are called isomers. Is that two isomers are ones that have the same molecular formula but have different structural formulas. And so this is something that you ought to be a little aware of, because if you say like they're making a particular drug, is that you can have two different drugs that have exactly the same chemical formula. They have exactly the same molecular formula, but they do two completely different things because their structures are different. In the same way that, I can take a cannon and I can use it to fire it at someone and do damage to someone, or I could take those same pieces and turn it into a flower pot. It does two completely different things depending on what you're doing with those based on how the structure is. Same parts, different structure. So I have sort of some examples down here of two different molecules here. And if we take a look at each one, you can sort of see on this first one, let's count the carbons. We have 1, 2, 3 carbons right there. So we know this is going to be C3 something. We have hydrogens. We have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So H8. And we have just one oxygen right here. So just O. So that's C3H8O. Then we have a different structure over here on the right. Let's count the carbons. It has 1, 2, 3. So C3. Then the hydrogens, it has 1, 2, 3, 4, 5, 6, 7, 8. So H8. And it has one oxygen, O, right here. And so C3H8O. It has exactly the same molecular formula as does the first one. These two are both identical, therefore, but these guys have different structures. So these are isomers. Turns out the one on the left is a type of propanol, which is an alcohol. The one that's on the right is not propanol. It actually is a type of ether. It is one that could be used, say, as an anesthetic. It would knock you out if you had to inhale it there. These two chemicals have two completely different properties despite having the exact same molecular formula, C3H8O. That's because they have different structural formula. They are isomers. So let's take a look. Just sort of be aware of that as we go through this, but let's take a look at how to solve some of these structural formula. So start off, C2H6. So first thing we have is we know we have two carbons. So I have a carbon out here. Now what we know for these carbons is we look at the periodic table, we see carbon has a valence of 4, so each carbon wants to make 4 total bonds. And so I have 1, 2, 3, 4 for this one, 1, 2, 3, 4 for this one. I have 6 hydrogens. Each hydrogen has a valence of 1, so each one wants to make 1 bond. Let's just take a wild guess here. Let's say there's an H down here, 1, 2, 3, 4, 5, 6 like this. That uses up all my hydrogens. My hydrogens are happy. My carbons, though, are short. Each one needs one more bond. And well, there's a simple solution to this. Since they each need one more bond, let's just join them up. And so we'll join this bond up right here. And so now this would be a proper structural formula for C2H6 because each of the carbons has 4 bonds. And we have 2 carbons. Each of the hydrogen has 1 bond like they want, and there are 6 hydrogens. So this would be the structural formula for C2H6. Let's look at our next one, calcium hydroxide, CaOH2. And so for this one right here, let's start off by looking at the calcium here. Our calcium, if you look at the periodic table, it has a valence of +2, therefore it wants to make 2 bonds. So it makes 2 bonds off the calcium. Our next part here is OH2. We know the oxygen wants to make 2 bonds. It has a valence of, -2. Hydrogen wants to make 1 bond. But this is a case where, remember we talked about polyatomic ions? This OH, since it's a polyatomic ion, means it travels together. That means we know that the O and the H are going to be connected. And so if I have an O over here, this oxygen wants to make 2 bonds, I know that it's going to have 1 hydrogen after it. And so I know for my other oxygen, when it comes off here, it's going to have its 1 hydrogen off of it because those OHs travel together. And so we got these two right here. But where will they connect? Each oxygen needs to make 1 connection to the rest of this whole thing. And, well, the calcium needs 2 connections. Each oxygen needs 1 connection. And so our most likely situation here is that these oxygens will connect to the calcium. And so we'll erase that guy for a second, and let's go ahead and put these in. And so that means we have an oxygen on this side, an oxygen on this side, and each oxygen, because it's hydroxide, is connected to 1 hydrogen. And I'll have to draw that guy down there. So if we look at this, let's make sure it works. We have 1 calcium, and each calcium should have 2 bonds, and this calcium does have 2 bonds. We have 2 oxygens. Each oxygen should have 2 bonds, and each oxygen does have 2 bonds. And we have 2 hydrogens, and each hydrogen has 1 bond like they like to be. And so these would be the ways, that's how you would draw out the structural formula of calcium hydroxide. Let's try one that's a little more complex as our last example here. C6H12O11, or sorry, C6H12O. So to get this guy to work, we know we have 6 carbons. And so let's try something out. Let's say we have 6 carbons here. So I have 1, 2, 3, 4, 5, 6. Let's just connect these guys up. We'll make a chain. Carbons like to form in chains. And so that usually gets you around. This is actually one of the reasons why these are called organic substances, because since they can form in chains, they can form basically as large of a molecule as they need to. And so they're used a lot in living things because of the fact that they like to form these long chains, because they can basically make just about whatever they want to, because these long carbon chains act like scaffolding, and it's sort of like building something out of Lincoln logs or something like that. You can just sort of put them together in whatever structure you want to. And so we have each carbon wants 4 bonds. We have 12 hydrogens. So let's see where these 12 hydrogens could go. And so let's put these, we got 12 on here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We still have 2 more bonds left for the carbon, and we have an oxygen which needs 2 bonds. So what can we do to get that oxygen its 2 bonds? Well, remember we talked about double bonds before. The oxygen could take a double bond, and so to do that, let's go ahead and take a look at what we've got there. So let's look at put our carbon back here. If it's going to double bond, it could double bond out here to our last oxygen. And so let's take a look at what we've got. We have the first carbon right here has 2 bonds to the oxygen, 1 bond to a hydrogen, 1 bond to another carbon for 4. All the other carbons have 4 bonds. All the other hydrogens have 1 bond, so everyone's happy about their number of bonds. We have 6 carbons like we should. We have 12 hydrogens like we should. We have 1 oxygen. So this would be a possible structural formula of C6H12O. Now, let's try another one. C6H12O. Instead of putting the C's in a line, I am now going to do them a little differently. Bond, 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 bond. We have a circle. It's called cyclohexane. And so each C needs 4. So we've already got 2 because they all connect to the other 2 C's. So we had 2 more. So they'll get their total number of bonds up here. So now each C would have 4 bonds here. I have 12 hydrogens. So let's put these hydrogens in here. So I have a hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I could put a 12th on there, but I'm missing my oxygen. I need to put my oxygen somewhere. So let's attach the oxygen out to this carbon right here. Whoop. And if I do that, then I've got that oxygen needs 1 more bond, right? And so because the oxygen needs 1 more bond, where's it going to go to? Well, that 12th hydrogen here. So by the time I'm done here, I have 6 carbons, each one with 4 bonds. I have 12 hydrogens, each one with 1 bond. I have 1 oxygen, which has 2 bonds. these two structural formulas are both acceptable ways of writing out structural formulas for C6H12O. These are just different isomers of that of C6H12O. I would accept either one for your answer, and it turns out there are actually about there are probably a couple dozen different isomers of C6H12O, any one of which is correct. So if you wanted to do this, this is in either one of these I would accept. So this is basically how you write out a structural formula. And so that's all we have for this lesson right here.